This is a Bendix G15, a full-fledged vacuum tube computer from 1956. And if saying computer from 1956 doesn't sound absolutely insane to you, check out the movie Blast from the Past starring Brendan Fraser. There's a moment where he absolutely loses his mind because he discovers that somebody has a computer in their house, which from the time period that he was from would have been absolutely unfathomable.
He has a computer in the house.
Thank you. But here we are, 1950s computer, and it's actually surprisingly small. I would say that this was maybe one of the very first mini computers or even personal computers in existence. Well, okay, personal computer is a bit of a stretch because when this thing released, it sold for $50,000, which sounds like a lot until you adjust it for inflation and you realize that that's actually closer to $600,000 today. And I realize that not all of my viewers are going to be familiar with how much US currency is, and so it's also equivalent to 80 million yen. So what am I doing with an 80 million yen machine hanging out in this office? Well, this particular machine is on loan from Bob over at System Source Museum. And if you haven't heard of System Source Museum, check them out immediately. They have one of the greatest collections of vintage computing on display in the country. And most of the machines are functional. You can get hands-on with unique, weird IBMs and Xerox Altos, and you can even see an original Apple I in person. And Bob is an absolute legend. So go check out System Source Museum and give Bob and everybody that works there a high five for me because they're all just excellent people. But Bob sent this G15 all the way down here to Texas to this office, not so I could have a very pretty paperweight, but so we could get it running and potentially be the only running Bendix G15 in existence, and quite possibly the oldest running digital computer in North America, which is a pretty wild superlative to throw around. And we are so close. In the previous episode, we actually got this thing booted up. There is proper code sitting in the rotating drum waiting to be executed, but when we tell it to execute, it executes the wrong thing. And I think what's holding us up is that we have some bad germanium diodes. I did some back of the napkin calculations on this, and I think it has around 460 vacuum tubes and nearly 3,000 germanium diodes in it. It's got a lot of them. And they're all chasing down 70 years old, so some of them are starting to give up the ghost. And we've already pulled and replaced about 3 of them, and we know that there are at least 2 more bad ones floating around on cards that we came across during our troubleshooting in the previous episode. But it seems really weird to say we know that there are at least 2 more and not have actually replaced them, and that's because when I measure them with my multimeter, they measure fine, but when they are in circuit, they don't work. And so that means that my multimeter is not putting them within the correct environment or conditions to see their failure mode. So we need a different, better way to test those diodes. And well, that's what we're gonna dig into today. So I have some pretty interesting ideas how to tackle this, but really we're just gonna do it the official way. So let's hop over to the bench and get started. I've got 3 diode cards on the bench today. I'm only holding 2 because I only got 2 hands, but I know for a fact that among these 3 diode cards, there is at least 1 bad diode floating out between them. The problem is that when I test them with my digital multimeter here, they all test totally fine. But if they all test fine with my digital multimeter here, how on earth am I going to go about figuring out which one is bad? And actually, more importantly, why do they test fine with my digital multimeter here? Well, the way that this thing does a diode check is by applying a small voltage in the forward direction and in the reverse direction. And we can actually kind of get a little bit of an idea of what that voltage level is by looking at the manual here. And you can see that for the diode measurement, it says the resolution is 1 millivolt and open circuit voltage is about 3.2 volts. The normal voltage value is between 0.5 and 0.8 volts. So that means that in the forward direction, it's probably only going to be applying around a volt to it. And in the reverse direction, at most, it's applying 3 volts. And well, all of these diodes at 3 volts are doing just fine. But we're not dealing with normal logic levels here. Minimum, the logic levels that we're going to see are 0 to negative 20 volts. But it's possible that these diodes are going to see much more than that. So we need something a little more aggressive to test these diodes. And you guys had a ton of brilliant ideas about how to test these diodes. And even my good friend Raymond over at arcadecomponents.com reached out and said that he has a curve tracer, which is absolutely the best way to figure out how these diodes are breaking down in the reverse direction. But the problem is one of scale. Like I said, I've got 24 diodes to check here, but these are not going to be the only diodes that are bad. We're going to run into a whole lot more that are bad. Like I said, there's about 3,500 germanium diodes in there. And if we're expecting at least 1% of them to fail, that's still a lot of bad diodes. So I need something that'll allow me to check these diodes quickly and under the conditions that are presented within the machine itself. And it turns out that Bendix was also aware of this, and they built something to do just that. This is a Bendix-made diode tester. I am worried about the problem of scale with these little guys here. And well, this diode checker is going to solve it. The problem with this diode checker is that no documentation exists. We can't find any official documentation for it, and nobody knows how to use it. So we have no idea how to use it. Oh, wait, nope, that's wrong. Let me rephrase that. We had no idea, and we had no documentation. But Lloyd, the absolute legend, sat down and reverse engineered this entire thing and wrote up a manual for it with a full-on schematic for how it is wired up. So now we know how to use this. We know what levels to expect. So we can start testing diode packs. And looking at it a little closer, it's pretty simple. The big obvious thing is that we have a little gauge right here in the center. This is a DC milliampere gauge that goes from 0 to 1 milliamp. And right below that, we have our test in R or F, so I imagine that's reverse or forwards. And then over here, we've got a big switch that we can rotate around to select the diode number from 1 to 13. We can also plug an individual diode into these banana plugs here and test that. So we can actually use banana plugs to test the individual diodes on something like this. So we can use this tester to test these cards, which is going to be fantastic. And then we have 4 slots right up here at the top, and they're labeled clamp, D1, D2, and D3. And these are the slots that you plug your card into. So this is a D3 card, for example. We would plug that in, and that's how we do our testing. Pretty simple device on the outside, at least. Let's take a look on the inside. I've already gone through and loosened up all the screws, so we'll just lift it up, flip it over, upside down, and there we go. Again, surprisingly simple, ignoring the obvious new technology that's hiding out right here. You can see this is the back side of the meter right there. Here's our test switch. Here's our 2 big wafers, and that's it. There's nothing else. We have 1 resistor here and 3 resistors up here, and the rest of this is just clever ways of interconnecting connections to test the individual cards. Really brilliant way to do that. So what's up with the piece of modern technology right here? Well, this is just a boost converter. Originally mounted underneath this metal clamp right here would have been a 35-volt battery. And this would have been the plug that goes into that battery, but those batteries are no longer available. And instead, we're just using a converter here to take whatever our input voltage is and bump that up to 35 volts. But ultimately, I think I'm going to run one of these little 4 AA battery holders. I'm just going to tape it down right there, run a little plug over to our little boost converter, and we should get this whole thing working perfectly. This diode tester is essentially 2 separate testers in one. You have the section that's set up to test the D1, D2, and D3 packs, and then you have a section that's set up to test the clamp pack. And the clamp pack is quite complex, and you need to test it in
multiple different directions, so it makes sense that that one needs to be a little separate. But it's important to note that no single two diodes are perfectly in parallel, so we can test each diode individually as long as we have the wires connected up correctly to the card edge connector here. Well, how are we testing these diodes to see whether they're okay or not? That's where Lloyd's excellent reverse engineering comes in, and I'm going to put a link in the description below to this document, so anybody that's curious about this diode tester can open it up and see what's going on. But he's got wonderful instructions here for how to properly use it and the values to look for, but he also goes into a lot of really excellent detail with simplified drawings of how each diode is tested. But we don't actually know what values specifically we're looking for because the original documentation doesn't exist, and we did some math and we were pretty sure that those values are the correct values, but it could be a little different. Bendix may want something different. They may be expecting a certain amount of leakage current that we're not seeing here. But we did recently find a pretty interesting document that our good buddy Rob scanned. And these are notes from field technicians from the 1950s, which is pretty wild. And they have some notes about the diode package tester. It says your diode package tester should be calibrated approximately every 2 months. Place a 300 ohm resistor on the tester between the posts to check a single diode. Read the meter with the switch in the forward position, and then all diodes that register above that value in the forward direction should be discarded. And then we switch over to a 470k ohm resistor, and all diodes that register above this value in the reverse direction should be discarded. So I need to find a 300 ohm resistor and a 470k ohm resistor, and then write down the values that I'm seeing out of this, and then that will be the ultimate values that we're expecting to see. There we go. I've just got 4 AA's stuck to here with double-sided tape. The wires go up, around, over to here. There's a little plug right here, and I can plug this in, and there we go. The buck boost converter over here is getting the voltage from the AA's, and it's producing 33.5 volts, which I think is actually what that battery was rated at. And this solution that Lloyd designed here with the 3D printed bracket to hold the boost converter is a really elegant solution. I think this is gonna work fantastically. All right, all back together here, and you can see that even without anything hooked up, our meter isn't exactly sitting at 0, but I've got a 470k ohm resistor here. We'll go ahead and plug that in, and we can see that the value looks like it's jumped up to about 0.09, and if I look at Lloyd's notes, he was saying that in the reverse direction, it shouldn't exceed 0.07. So I think I can actually adjust that with this little screw right here on the front. And if we come down to about there, that's 0.07. So nothing should ever go beyond that when in the reverse direction. So next, let's hook up the 330 ohm resistor here. I didn't have a 300 ohm resistor, so 330 is going to have to get the job done. With it hooked up, we're pegged off the scale, but if we go there, we can see that's like 0.22, and Lloyd's notes were saying 0.28. 0.28 might make a little more sense with the 300 ohm resistors. So I think we can be pretty strict on it. If we see anything above 0.2 in the forward direction, we might want to consider that that diode is doing a little wonky stuff. And check this out. I got curious what the diode test was actually using for voltages here. And so I've got my multimeter here on DC on the individual posts that you're used to test a diode. And we can see it's showing 33.3 volts in the reverse direction. So that's putting 33 volts right on the face of that diode. If I go in the forward direction here, it goes to minus 24.1 volts. So that is going to be flipping the polarity so we can see what the voltage drop across that diode is. All right, let's take this thing for a test drive, and in the process, I think the simplified diagrams that Lloyd drew up for us here are gonna make a whole lot more sense. So right now I've got a D2 pack in it. This just has 7 individual diodes on it, and we select which diode we wanna test using the diode number switch over here. So right now it's set to off, but if I flip it over to 1, we are now actually testing the number 1 diode, which is right on top here, in the reverse direction, because our little test here is sitting on R. And we can see that the meter shows essentially 0. And if we look at the simplified diagram, that makes perfect sense because the diode is blocking the return path for the ammeter. There's no way for current to flow through the ammeter unless the diode has significant reverse leakage. And if it does, then we'll see the ammeter start to move. So now if I want to test forward, I just push this over to F, and we can see the meter moves a little bit, but really not all that much. And at first that didn't make sense to me, but again, Lloyd coming to the rescue with the simplified diagram here, we can see that the diode is providing a current path back to ground that bypasses the ammeter. However, if the diode has sufficient internal resistance, it's going to shunt some current over to the ammeter. And we're expecting that because diodes have a certain amount of forward voltage drop. But if the internal resistance of that diode is too much, or it has too much forward voltage drop, it's going to shunt more and more current over to the ammeter. That's why whenever we test this in the forward direction, if it goes too far, that means that the diode has too much internal resistance and it's shunting too much current over towards the ammeter. And essentially what we're looking for is absolutely nothing in the reverse direction, and if the diode were perfect, it would be nothing in the forward direction. But we're expecting a little bit in the forward direction. So actually this is kind of what we're expecting every diode to do. So let's check the next diode in line here. And I tested these beforehand, so I actually kind of knew this was coming. This is diode number 2 in the reverse direction. And you can see we bumped all the way up to about 0.18 milliamps cutting across the ammeter. And again, if we go back to our reverse test simplified diagram here, that means that the diode is allowing some current to pass back to ground through the ammeter. That is no good. But if we check it in the forward direction, it drops down to normal. But that's unacceptable. So diode number 2 is bad here. So if we just burn through the rest of these, there's diode 3, that looks good. 4 looks good. 5 looks good. 6 looks good. And 7 is real bad. 7 is just shorted, apparently. That means that we just have a straight connection through. But in the forward direction, it still seems to be okay. But yeah, in the reverse direction, it's just breaking down immediately. So on this particular diode card, diode 2 and diode 7 are bad. So the next step is just pull out every single diode card in the machine and do the same test here. I normally don't like doing large-scale testing of a single component like this, but in this case, I think we have a really good methodology. And given that that last D2 card had 2 diodes that were bad, I think this makes the most sense. The diode tester really allows me to fly through testing huge numbers of diodes, but there's so many, it's definitely going to take a while still. So I fired up the laptop and hopped onto the Discord live chat just to hang out and chat with people while I tested diode cards. Normally I do a live chat every Friday night at 9:30 Central Time, but that time doesn't line up very well with Europe, which means I rarely get to chat with my fellow European nerds, and this was an excellent opportunity to catch up with them. And I'm not going to pull any punches here. Y'all are a little crazy. Y'all are a little out there, but I had an absolute blast chatting while I burned through diode testing. So thank you guys so much. That was a ton of fun. But after identifying far too many bad diodes, it was time to get to replacing them. Since the Bendix PCBs don't have any solder mask, I could remove the bad diodes fairly easily by heating up the pad, then grabbing the diode leg with a pair of needle nose pliers and just pulling it up and out. The new diodes I'm replacing this with are BAT41, or I call them BAT41 Schottky diodes, and they are good to 100 milliamp continuous current and 100 volt reverse voltage, and they have very similar forward voltage drop to the germaniums. I could probably get away with more traditional silicon diodes, but I've used these BAT41s in a few places already where we had bad germaniums, and they work totally fine. So, you know, stick with what you know works and all that jazz. There we go. Nearly 60 diodes identified as bad and now fully replaced. And this Bendix diode tester worked like absolute gangbusters. I tested more than 3,000 diodes on this thing in like a day and a half. And I can't think of any other method of testing diodes that would have afforded me the speed to get that insane job done in as short a time as this did. So if you're bringing up a Bendix G15, and I know that there's
probably like less than 10 of us in the world that are doing this right now. But if you're bringing up a Bendix G15, I would say one of these is an absolute necessity. This thing is absolutely fantastic, but I could not have done this had Lloyd not gone through the work to fully reverse engineer it and come up with stunningly good simplified diagrams, a full schematic, and an excellent manual for how to use this thing. So Lloyd, thank you so much for that. And with all of these diodes now replaced, I mean, that means that we had like 50 plus logic gates that were not functioning. We had 3 flip-flops that were not flipping and flopping. We had a write amplifier and a read amplifier that weren't working correctly. That is a large amount of the machine that would have not been functioning correctly. Now granted, there's like 3,000 diodes in this thing, and for 60 to be bad, that's still a phenomenally good yield. So these germanium diodes are pretty tough, but that's a lot of functionality that would have been left on the table and not working. And so yes, we were getting through the boot up process, but it would have taken a long time to diagnose and find all of these diodes one by just tracing it out on the machine whenever something didn't work. So with all these now replaced, I think it's gonna really dramatically change how that machine behaves. So I want to thank you all so much for watching today, and I hope to see you in the next episode. That usually works. Is it because when I put my hand down, I hit the diode pack and that made a funny noise? Let's try that again. All right. So I want to thank you all so much for watching, and I hope to see you in the next episode. You're still here. So I guess that means we're not done yet. I suppose that we've come this far. You guys want to see me plug all of these back into the machine and flip the power on and see if it behaves any differently. I mean, that would make sense, but I suppose that I should also say that I very easily could have made it worse. It could absolutely not boot at all, and that's kind of a terrifying thought. But I don't know, you're right. We've done this much work. Let's plug it all in, put some power on it, see what happens.
I'm quite nervous about this because, well, I said it before and I'll say it again, I absolutely could have made it way worse here. I could have broken a diode while I was trying to repair other diodes. I could have broken traces. There could be a solder blob causing a short. A lot of the cards got shuffled around because I didn't keep track of which slots I pulled them out of. I could have made a million mistakes that actually has made us take a couple of steps backwards. So I am very nervous about this, but I've got the scope set up here. We're triggering off of T0. If we see data coming into M19 and filling up like a shift register, the number track initially, and then the tape reader light kicks off, and then we see the first block of data off of the diaper feed into that, that'll be essentially where we left off in the previous episode, and I would consider that a win. So that's all we're really aiming for here. Anything beyond that is bonus points. So fingers crossed. Let's hope we see data filling up onto M19 here. I'm gonna go ahead and push DC on here. There we go. Paper tape reader kicked off. Data is not being fed into M19. We never stopped reading. I made it worse. I broke something. Oof. All right, well, we're gonna go ahead and pull this off before it just spools the entire spool. All right, troubleshooting shall ensue. It is several hours later, but check it out. If I push the reset button here, it kicks off. The paper tape reader should start going here shortly. There it goes. And we should see data filling into M19 properly. There we go. Shifting in like the shift register it is supposed to be. This thing is booting exactly like it was in the previous episode. So what went wrong? Well, I actually had to talk to Lloyd. We jumped on a Zoom meeting and troubleshot this thing for a couple of hours. And here it is. This is it. It's not even diode related.
we had a tube that lost a filament. So this lost one filament. The other filament was still fine, but I could visually see that one of the filaments had gone down. And this tube was in one of the flip-flops. And when I checked the diodes on the flip-flops, I pulled all the flops out, checked them on the bench, and then put them back. But I didn't put them back in exactly the same place. And when I put it back into position A1, which is the CY flip-flop, which controls the flow of data onto the number track. So that was just screeching the entire thing to a halt. Number track was never resetting, and if we didn't have number track resetting at the very beginning of startup, it was preventing any data from ever making it to the drum. So we're fully booted up now. However, I've tried this, but it doesn't do anything. If I flip the go button over here, nothing happens. We don't even have any blinking lights anymore, but we do have some good news in that our command line is saying 23 here, which is exactly what the command line is supposed to say. So it knows where the next instruction it's supposed to grab and execute is, but for some reason it's not jumping there and executing it when I flip the go switch. So we may still have a few faults going on in some places, but well, I don't know what they are, but it's going to take a lot more troubleshooting than I have time to dive into it today. But I think this is pretty awesome because we've probably eliminated a bunch of problems that were lurking in the shadows. And while yes, we do still have problems, we should have fewer problems. So in the next episode in the series, we're going to dive in hard on troubleshooting this. But that next episode isn't going to be next week because I'm jetting off to Pittsburgh to hang out with the guys up at the Large Scale Systems Museum. And on October 25th, they are having a fundraiser. All funds generated at that fundraiser go towards keeping that excellent museum alive. So if you have the means and you have the time, come hang out with us at the Large Scale Systems Museum. In the meantime, I'm going to turn this thing off because I'm starting to sweat profusely. 460 vacuum tubes puts out a lot of heat. So I want to thank you guys so much for watching, and I hope to see you in the next episode. It's working this time. It's working this time.